I'm going to talk about storage a bit. I'm going to talk about myself as well. So I've been here before. Some of you, had me at some point. But so when I talk with the students now, I say I'm old because I am. So I was here in 2001, and most of the students were not born at that point. So I went back on the Internet Archive and found the announcement of my position in June 2001. I was at this lab then with Eric, and a few others. So now I'm back as an experienced professor, and I'm old enough so that I've been asked to teach early on. So I'm going to talk about teaching a bit because it's been taking a lot of my time. It's been decided that I should be course responsible for programming and problem solving, which is the what used to be that null, which has been POP for about 10 years. So I've taken it over, and in a world which is slightly different than it used to be because of ChatGPT and the Gen AI application. So the way we talk introduction to programming has to change, and I believe it can be for the better. So if we look at the, I'm going to. So if we look at the important part of problem solving, you start from a problem, you write the specifications for your functions, you write the code, and so you have the tests. So you write the test or you run the test. Historically, the focus has been very much on the specification to code transition. So you were given specifications and you had to write code. The problem now is that if we keep on doing that, then we'll have a generation of students with a very high grade in introduction to programming because they'll be using Copilot or whatever Gen AI tool. So this part is no longer the hard one. So writing code is easier today. Reading code is a bit harder. So this is what we focus on. And so in terms of focus areas, the fact that this is easier, that writing code is something that we take for granted. I take for granted that students are going to use ChatGPT all over, even if I don't want them to, but they will. So we try, so Fritz is very much involved. So we try to take that into account and focus on strategies for problem solving, how to design functions given the strategies. So we introduce concept. We use F# as a first language so I've been talking about functional programming for a month now. Next week I'll talk about imperative programming for the first time. And we used F# to introduce some of the concept. We'll use Python in the second step so that they can see the concept in a different setting. The focus is on reading code, not on writing code, so modifying existing code. Also because I think that's closer to the way people actually work in practice. We focus on breaking code. So given a function, how do I break it? How do I make it not work? And we focus on specification-based testing. So the fact that writing code is less of a problem gives us the possibility to focus on slightly more advanced or slightly more, so some topics that Fritz has been wanting to work on for some time, argumenting for a long time. Now I think we have the possibility to make it happen. The first slide, one of the first slides I used, it's in Stope. This class, the programming and problem solving, is actually, I think, the largest in the science faculty. So it's 470 students from 4 different lines. So they're about 330 every week in the auditorium. And so it was important for me to start, to tell them about DIKU, about the history, so I start with Peter now. So there are a lot of things to like about this code. What I really like is the fact that it's talk about program. So it talks about what is in the mind of the people. So it's not just code. Programming is not code. Programming is a theory, is whatever you have in your mind. It's exchanging with others. But it's also running your programs on a computer. So so we put an emphasis on why reading code is hard. So what is hard about understanding code? But I started by explaining what a computer was. because you don't write code for any type of computer. So we will live in a world where many students have no idea of what a computer is. They're on the cloud, they're very abstract environment. I think it's very important to ground everybody and start with what a computer is. I'll get back to that because my research, a lot of my research is about hardware, software, co-design. So going away from the assumption that you write code for an existing computer, but given a workload, you're going to define the computer which is going to be best for your workload. So that's the machine I use so that's a machine. We have a bachelor project working on this. It's a RISC-V based server, the first one. So it's one of the pioneer box from the RISC-V Alliance. It's 64 cores. So RISC-V, 64 cores, 128 gigs of RAM. So it's a pretty interesting machine, and so now we're benchmarking and see what the limitations and the possibilities are. Because of the title, so that's a computer, and I use that to explain, what's the memory, what's CPU, where storage. If we focus on storage, because that's what I do, I had a keynote in June, so I found some slides about how SSDs looked like 10 years ago. I started working on SSDs in 2008. I was still at DIKU. I had a project in Greenland. That was the MANA project. So in Greenland, we had to store data, and it had to be operating for. So it's in Zakkenberg, so northeast Greenland. The device had to be operating for an entire year by -40 and down to -40 temperatures, and so hard disk drive. So the temperature is out of the operating range for hard disk drive. So I had to start looking at SSDs, and so it was relatively early, and this has been the red line in my research since then. So 2014 is a few years after 2008, but this is the first NVMe drive. So from Samsung. So it's PCIe Gen 3, so 1.6 terabyte capacity, some 750 kiloops in terms of random reads. Today we have data centers SSD, so the hyperscalers are driving a lot of the innovation and actually a lot of the research agenda as well. So this is a device which is only available to hyperscaler, and we actually have access to it through Samsung Research Cloud. Performance has improved not by orders of magnitude, but there's been a lot of evolution, and we've been contributing. I mean, I've been so lucky to work with very smart students over the years, and we worked on some of the systems that Jakob mentioned. So I won't get into the details. The point is that there's some consistency in the line of research I've had for some time. What I'm most happy about is the fact that Copenhagen is now the center, one of the centers. I could argue is the center. I mean, there's South Korea and there's Copenhagen in terms of innovation in the ecosystem around storage systems, modern storage systems. Both Western Digital and Samsung have research centers here. I believe more than 50-60% of the staff in those companies here in Copenhagen are from DIKU. The rest are students from ITU. So, Sarabia, Joel, Simon, and Klaus did a PhD with Brian. Jesper did his master with me. So the point is that those guys, so there's some close ties with the environment, and there's a lot of them are contributing to the Linux kernel. So there's a possibility for students who are interested in systems. So back in the days, there was this lab. You could do very good work with this lab, but in terms of work, now you can do research and project in the systems area, and you can join a team of leading software engineers working in the area. Just a word about my current research. So I've been working for some time with a colleague, Alberto, from Freiburg, about. So we had a tutorial and we wrote a book. It took a long time. We're fighting the publishers right now about copy editing. I'm happy to talk about that if anyone is interested. So the idea here is that we're looking at the evolution of storage devices from conventional SSDs to reprogrammed SSDs, where some of the internals of the SSDs are being redefined. Computational devices, where some additional computational unit is added to offload from the host. And what we call co-design devices is a combination of both, where we replace internal subsystem, possibly with application logic and computational capabilities. We are in a position where we've taken over a project from Korea called OpenSSD, where we now have an understanding and the capability to actually develop all the components of an SSD on experimental boards. So we have FPGA-based platforms. So we are developing our own SSDs, and this is not just paper. We now are able to experiment with this type of device. And part of the resources are coming from some projects. We're still in a negotiation phase, so I cannot say much about it. But I can look forward to having people work on a project where we start from component integration. So the idea at the European level is that digital autonomy is strategically important. We need to have European software and European hardware. So there's a portfolio of projects integrating European hardware, RISC-V in particular, but also the RIA ARM-based processor. And we're developing, doing component integration, developing boards, and the idea is to have an accelerator-based architecture. So co-devised SSDs, smart NICs, which can offload processing from the processor using European hardware. And that's part of what we are going to work on in the next few years. So looking back, moving forward, so I found some slides from 2003. So you might recognize some of the people here. I mean, Eric is there. So Johan is actually working for Western Digital now. Anyways. But so the thing is that there's some consistency also in terms of the type of projects, the type of research we want to do based on systems. So system design, implementation, evaluation, cool hardware platforms, experimentation, applied problems, and hard work. So that's part of why I'm very happy to be here and having the opportunity to work on those problems. Thank you very much.